Let's look at our next example. This one is more practical. It has to do with driving. And it's also a very more interesting problem because it involves not only just normal force and gravitational force, it also involves friction. So we're going to look at how friction plays a role in providing the centripetal acceleration. What we have here is a freeway exit ramp. You know, as you drive off a freeway, you have to take an exit ramp, which is curved. And for simplicity, let's say it's part of a circle of radius r. So basically, the car is doing a circular motion about a horizontal circle centered at point O. Okay, and so you know the ramp is curved, but also the ramp is also typically banked, which means the road is inclined. You know, it's not horizontal. It's not horizontal. Let's look at what happens. Here is a rear end view of the car. So the car is going into the the paper forward, and which we're looking at from behind. So the car moves in like this. Here is a cross-sectional view of the road. Okay, the road is inclined like this. The car is doing a horizontal circular motion centered at point O right here. Okay, it goes around like this. Let us draw a free body diagram for the car. Of course, you have a contact force N from the road. We have a non-contact force mg. Is that all? Well, what about friction? Right? Generally, the road also gives you a friction. Let me first ask you, is this static friction or is this kinetic friction? Please be very careful. Well, you know that a lot of people would say, well, this is kinetic friction because after all the car is moving, right? What is the condition that determines whether a force of friction is kinetic or static? Well, when you have to look at the two surfaces making contact. Is one surface sliding against another surface? In other words, is there any relative motion? If there is, it's kinetic. If not, it's static. Under normal driving condition, the tire that's touching the ground, is the tire slipping against the ground? It's not, right? So, at the contact surfaces between the tire and the ground, there is no slipping going on. Therefore, it is actually static friction that we have to look at, not kinetic friction. Okay, what is the direction of that static friction? Well, you know, static friction is always against the tendency of motion, right? So if you park your car on a curved bank like this, of course the tendency is to slide downwards. Therefore, the static friction is always upward. Okay, now you're not parked, you're actually going in a circle. You can imagine what happens. You know, if you're going very slowly, okay, extremely slowly, that's almost like you're not moving, right? So the tendency, of course, is to slide downwards and the friction will be upward. As you go faster and faster and faster, what happens? Well, you know, when you go really, really fast, the car has a tendency to actually slide uphills, right, instead of downhills, right? In that case, friction will be automatically reversed and will try to pull you in a downward direction. So therefore, friction actually can change both its magnitude and direction. Is this a bad thing? No. It's a great thing because it is a variable force. It varies in accordance with how fast you drive. It automatically adjusts itself, of course, within its limit, right? It can adjust itself so that you don't have to drive at one given speed anymore. If there were no friction, these would be the only two forces on you, on the car, and I can tell you, this is very, very dangerous driving because there is only one speed that make it work. Okay, if you have no friction, no traction from the road, that is, the road is extremely slick, you will end up being able to drive only with one possible speed, which we will find first. Let's find that speed. Okay, what is that one speed you can negotiate a curve with if there were no friction or no traction from the road? Well, you got only two forces, right? N and mg. Look at what happens. Okay, here is the angle theta. It does a horizontal circular motion. We know how to do that. It's a similar case with conical pendulum, except you replace t with n. So we have a similar deal. Okay, in the horizontal direction, I have n sine theta. That is the horizontal component of the net force, and that equals mv squared over r, right? mv squared over r. R is the radius. In the vertical direction, there is a component of n going up. That's n cosine theta, and that must cancel with mg downward because it doesn't move up and down vertically. Okay, you can cancel n by taking this divided by that, so you get tangent theta here, and m cancels, so the mass of the car does not even matter. Then you have tangent theta equals v squared over gr. What did that tell you? It tells you v equals the square root of gr tangent theta. See, there is only one solution to this problem. You must drive at precisely the speed of gr tangent theta. If you go faster than that, so v is greater than that value, that means you would require greater n to balance this equation, right? A greater n would make this side greater than mg though, so what's going to happen? The car is going to slide up hills because the net force is upward. On the other hand, if you go slower than that, then v is too small for this equation, so n is less than that, and therefore there is not enough upward supporting force n, and therefore you're going to end up going down. You're going to slide downwards. So you see, without friction, driving becomes very dangerous because you have to drive at this one speed. Now, what happens with friction? Let's look. Let me draw a fresh free body diagram including friction into consideration. So again, I have this car, right? Let me simplify it into a box. I have mg, I have n, but I also have friction. What is the direction of friction? Well, let's look at a situation where you drive so slowly that the tendency of the car is to in fact slide downhills, okay, because it's almost like it's not moving. To slide downhills. That means friction being opposite to it must be uphills, like this. This is Fs. Static friction, okay, not kinetic friction. Let us draw a coordinate system. You know the thing goes in a horizontal circle like this, right? So therefore, it is wise to choose a horizontal coordinate x and a vertical coordinate y. So that along the x direction, I have the net force being equal to the centripetal force. In the y direction, I have the net force being equal to 0. Alright, so I have n. This angle is theta, so is this angle. Let us apply Newton's second law again. In the horizontal direction, this time, I have n sine theta. That's inward. It points this way, which means point toward the center of the circle. The center of the circle is somewhere here, right? So I consider this positive. Fs has a component, horizontal component, that goes outward, which means it's negative. So minus Fs. What does that equal to? That equals mass times centripetal acceleration, okay? Because, you know, the net force points toward the center of the circle. That is needed to do a circular motion, so it's mv squared over r. In the vertical direction, what do we have? The net force is equal to 0 because it doesn't move up and down. Okay, so I have n cosine theta, right, plus a component of Fs going up, and that is plus Fs sine theta. Oh, by the way, I forgot a cosine theta here. Fs goes this way, I must multiply cosine theta in order to get outward component horizontally, cosine theta here. Okay, please add that. That equals what? mg, okay? Because you add these two upward components, it has to cancel with the remaining downward component, which is mg. Now, what are we looking for? We're looking for v. What kind of speed can I drive with? You know, there is not a unique solution to it because I don't know what Fs is. Some say, well, I know what F is. Isn't that equal to mu s times n? Well, let me ask you. Is it true that Fs always equals to mu s times n? When is it equal to mu s times n? Well, we learned from the previous chapter that Fs can vary between 0 up to a maximum value. What is that maximum value? That is mu s times n. Okay? Now, when the force of friction, static friction reaches maximum value, what does that tell you? It is on the verge of starting to slide, right? But nobody's telling you you're driving on the edge, right? You don't have to drive on the edge. So Fs can vary between 0 and the maximum value, which is mu s times n. I don't know what it is. And that's a great thing, because what you do is, within the limit of Fs, you can drive at whatever speed you want. You know, let's say you drive at a certain speed so that Fs equals half of its maximum value. That's great. If you drive a bit slower, it turns out that Fs equals to 70% of its maximum value. That's great. You know, so Fs being a variable is a great thing because it gives you a way to adjust your speed. As a matter of fact, you know, without Fs, you have to drive at a certain speed. That's the speed. If you go any slower than that, you're going to slide down. Okay, but with Fs, let's see what's the minimum speed you can get away with. Okay, so because you know you get a force pushing you uphill, so that helps you, right? So that you can afford to drive a little slower than that. How slow can you get? Well, you know, suppose you're driving at minimum possible speed. You're going so slowly that you're almost going to slide down hills, and therefore friction is doing everything it can to help you. Therefore, friction has reached its maximum value, right? So for V minimum, the minimum possible driving speed, so you must set Fs to be equal to its maximum value. Of course, its maximum value is mu s times n. Okay, that's when friction is at its maximum value, you're about to slide downwards. You plug that Fs equals mu s n in here. So this term is now mu s n cosine theta. That term is mu s n sine theta. You see you got n here, n here, n here, n here. You're looking for v. You don't want to know what n. You want to eliminate n. What's the simplest thing to do? Is to take one equation, divide by the other, so that you get n, 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 and they cancel out. Okay? So please plug Fs equals mu s n into here, and then take the first equation divided by the second equation. Let's see what we have. Okay. N is gone, right, when you take division. So what you left here is sine theta minus Fs is mu s. Again, n is gone. There is cosine theta left. Cosine theta. Okay. Divided by what's left here. N is gone. Cosine theta plus F is mu s n. Mu s is left. N is gone. So it's mu s sine theta. And what is that equal to? That equals to, you take this divided by that. So you see the mass of the car doesn't even matter. Okay. M and M cancels. That's v squared over gr. That is the minimum speed. So what is the minimum speed equal to? You work it out. You find that v minimum equals to the square root of gr times this thing here. Okay, let me copy it. That would be sine minus mu s cosine divided by cosine plus mu s sine theta. So this is the minimum speed you can drive with the help of friction. Let's compare with what we got before. You see, that was the case, that was the speed you can drive in order not to slide downwards. Our speed should be less than that speed because we have some help from friction to help us stop from sliding down, right? So this v minimum should be less than that v. Is that true? Yes, it is, because look, you have sine over cosine. If you don't look at mu s, don't you have just sine over cosine? That's tangent, right? But now you have sine minus something, so the numerator is less than sine theta, but the denominator you have plus, so it's not just cosine plus. So you have a smaller numerator and greater denominator. Of course, that is less than that v. Okay, so that's less than gr tangent theta. In fact, it becomes equal to gr tangent theta only if mu s equals 0. But of course, when mu s equal to 0, it's just like you have no friction. So it makes sense. Our formula goes back to this case when you set mu s equal to 0. Okay, so this is the minimum speed you can drive with. Okay, now imagine you go a little faster. If you go a little faster, then friction will no longer be at its maximum value. Because think about it, you go faster, right? You go faster, require greater amount of the net force going this way because v is greater. That means the acceleration, centripetal acceleration is greater, so you need a greater net force going this way. And since Fs is against that, you want to reduce Fs. Okay, so the friction is no longer at its peak value. It gradually gets smaller and smaller and smaller. As a matter of fact, if you drive at a speed of gr tangent theta square root, then the friction becomes 0. You don't need any friction. Okay, now what happens if you go faster than the square root of gr tangent theta? Then the tendency is now reversed, right? You have a tendency to slide upwards because you're going so fast, okay? You're going so fast that even when you set f is equal to 0, n itself alone is not enough to provide an inward push to give you the necessary centripetal force. You need more centripetal force than that. So now you have a tendency to slide up, and friction automatically reverses direction to help you so that it prevents you from sliding upward. Okay? And as you go even faster than that, friction becomes even greater, and even faster, even greater, until at some point you're going so fast that friction again has reached its maximum value. It is just about, you're just about to start sliding off, up the hill. That is when you're going with the maximum possible speed. Any faster than that, you start to slide up hills. So the question is, what is that maximum possible speed? You can redo this problem from scratch to find the maximum possible speed instead of minimum. But is this really necessary? Well, think about it. If you redraw the free body diagram when you're moving at the greatest possible speed, V maximum, not V minimum, you can still draw the same mg, the same n, but the major change here is that Fs has to be reversed, right? So F is not like that. You see? Okay, so what about the magnitude? The magnitude is still the same expression, mu s times n. Okay, mu s times n. So you didn't really change the expression for its magnitude. You just reversed its direction to go from the case of minimum speed to the case of maximum speed. Okay, so how do you change the equations accordingly? Well, this will have to be plus sign, this will be minus sign, right? So you can, just change the signs. How do you keep track of these sign changes? In fact, the only signs you have to change are the signs in front of the friction term. Okay, the friction term. And the friction equals mu s times n in this case. So there is a mu s here. So you see, you only have to change signs whenever you see a term that has to do with mu s. That's how you reverse the direction of friction. Okay? Now, this is equivalent to changing mu s to negative mu s. You see that? Because even though mu s is really not negative, but when you add a negative sign, whenever you see mu s, you are actually effectively reversing all the force directions that concerns with static friction, which is exactly what we're looking for. We have to reverse this direction from here to there. So by setting mu s to negative mu s, you can effectively go from V minimum to V maximum, or go from V maximum to V minimum. Okay, so that's the simplest thing to do, is to change the sign in front of mu s. We have this expression already for V minimum, so let's copy that to get V maximum. We don't have to start from scratch. Okay, let's copy that. Here is V minimum, right? V minimum right here. So how would I write V maximum now? Remember, I just did reverse mu s to negative mu s. So there we go. V maximum equals 2. Square root of gr, same thing. Sine theta plus, right? Not minus, but plus, because mu s is now negative mu s cosine theta. And then divided by cosine theta minus, right? Minus mu s sine theta. That is V maximum. Okay, now that is really good because with static friction, again, we have achieved this flexibility. We can drive with any speed between V minimum and V maximum. We'll be safe. Indeed, V maximum is greater than V minimum because look at the expression here. I have a positive term in the numerator, negative term in the denominator. That means I'm faster. I have a greater overall value here, so V maximum is greater than V minimum. Okay, so that makes perfect sense. Just one last thing here, you notice. Sine theta minus mu s cosine theta. This term can be equal to 0. When this term equals 0, V minimum is equal to 0, which means you don't really have to drive at all. The car is not going to slide down by itself. Why is that? That is because tangent theta equals mu s, right? Because sine equals mu s times cosine. Remember that formula we learned from last chapter? What happens when tangent theta equals mu s? You have what's called a critical angle, right? When you park your car on a slope with critical angle, it's going to stay put by itself, right? So that means static friction alone can sustain the car. It's not going to slide down. You don't have to move in order to stay at rest. In order to stay on the slope so that you won't be pulled down the slope by gravity. Okay.